Alright, so based on the sequence data as well as the representation we introduced before, next we can introduce the recurrent neonates or the RN model for you in detail. We know this RN is used to model sequence data, right? So therefore the architecture of RN is also like a chain actually. So formally we can represent as a recurrent neonate with one single hidden layer in something like this. So you can see, we have the input layer, which will be denoted by the X. We also have the hidden layer denoted by H, as shown here. And we also have this output layer, which is denoted by O, as shown here. So the architecture seems to be very similar to the multi-layer perception. However, the main difference will be, for the hidden neurons in the same layer, they will also have this input and output relationship. Now for this neuron, it receives inputs from both this input layer, the X, as well as inputs from the nearby neuron in the same layer, like in the input from this neuron into this one, right? So for this neuron, it will receive input from two sources, from both the raw inputs as well as other hidden neurons. It will also generate outputs to both the hidden layer, to nearby other neurons, as well as to the output layer. So you can see if we take a look at the hidden neurons in this layer, it will be forming something like a chain, right? It will be like a chain. As to the inputs for the model, we have both xt, xt minus 1, xt plus 1, and etc. So they denote this ordered inputs from some sequence data like text, right? Given a document according to the orders of words, we can feed these words as inputs into these recurrent neonates. As to, for the representation inside a recurrent neonate, we can take this neuron as an example, right? We can take this neuron as an example for this ht, and we can update this ht, its representation or this vector as the summation from both source, as a summation of inputs from this source as well as from the hidden neurons. So for this ht, it receives two inputs, and the inputs are parameterized by different parameters, now u for the raw inputs and w for the hidden neuron inputs. So we can represent this ht vector equals to ux, u is something like a matrix or the parameters, times this x vector, plus this w denoted by the parameters, and times this h vector, plus the bias. And then we can further feed this one as input for activation function like sigma function as shown here. In this way, we can calculate the hidden representation of the neuron ht, combine both the raw inputs as well as other hidden neuron inputs. So this u and w, these are the parameters which will be shared inside this model. In other words, for all the inputs, the parameter connecting the raw inputs to the hidden neurons, they will all be parameterized by the u, this matrix, the parameters. As to the connection among different hidden neurons, their parameter will be denoted by this W matrix. And then based on the hidden representation of this ht, we can further calculate the output, like OT, for example. So for the OT denoting the outputs for the hidden neuron, and it will receive inputs from this ht is a hidden neuron, right? And the connection between them will be denoted by this V matrix, these parameters. Therefore, we can denote this OT equals to the sigma inside we have V times HT plus the bias term. In this page, we just take this HT and OT as an example. In a similar way, we can also calculate this HT minus 1, HT plus 1, as well as OT minus 1, OT plus 1 in a very similar way. So you can see for this model, it receives all the inputs. However, for all the hidden neurons, it receives the inputs from the previous hidden neuron as well. And you may also wonder how about the neurons at the very beginning. When the xt minus 1 is the first word input, how about its inputs from other hidden neurons? If this one is the very first neuron, then the input from the previous hidden neuron will be assigned with some default value instead. But it will calculate this representation of both hidden neurons as well as output neurons in a sequential way from the beginning to the end. Because for the later ones, we have to receive the input from the previous one. Therefore, we have to calculate the HT and the OT in a sequential order from the beginning to the end. So this is a recurrent neonate. Inside, this chain structure is very unique because they will create some connection among the neurons even they are in the same layer. So in this recurrent neonate, we just provide you with an example with one single hidden layer, and they will share the weights, U, W, and V, right, for different input neurons and the rest hidden neurons. Actually, in the real world, we can also build a very deep recurrent neural net with a very deep architecture as well by incorporating more hidden layers. In this page, we show you the recurrent neural net with more hidden layers. We still have the inputs, this X as the inputs, and they are ordered inputs like text or documents, right? And inside the model architecture, we have multiple hidden layers, like L different layers as hidden layers. We have H1, H2 layer, and HL layer, right? So for the neurons in the hidden layer, they will receive both inputs from the lower layer, this one, right, to this one, as well as the input from the neurons in the same layer, but before the current neurons, not from here to here, right. Similar for this one, it will receive input from the lower layer as well as the one before it, right, in the same layer. As to the neurons in the output layer, it will receive the inputs from the hidden layer, the final hidden layer, and then we can calculate the outputs. So for the neurons in this deep recurrent neural net, we also calculate the representation of both hidden neurons as well as output neurons in a sequential order from left to right and from bottom to top. In this way, we can provide the calculation of the hidden representation of the inputs into the hidden neurons as well as the corresponding outputs. And you may wonder, how can we use the recurrent neural net to, in real-world applications? What will be the real-world application architecture? Do we have always to build something like this? So actually, this recurrent neural net may have different forms. In this page, we can provide with some illustrations about different forms of recurrent neural net in the real-world applications. And we may have some forms which we have one single input or one single source of input, and we also generate one single output. And we can represent the RNN in this kinds of structure as this one-to-one RNN. It has one single input and one single output. It will be very similar to the MLP model we showed before, right? So for example, we can utilize the RNN in this structure as a model for some task like image classification. Given the image input, we can calculate its output labels for the image, right? It will be very similar to the MLP actually we showed before. Besides one-to-one, we can also have one single input, but we try to generate multiple outputs. If so, then we can try to build a RNN something structure like this. We have one single input. However, we try to generate multiple outputs, and inside we can have a hidden layer within the chain structure. It will also have multiple hidden representations corresponding to the outputs. And we may apply this kind of application to some real-world problems that try to generate the caption for an image. We can provide the image as one single input source for this RNN, and we try to generate a sequence of token or words as a caption for this image, right? So we can have one single input, however, we try to generate a sequence of words or many words as description for this image. Besides this one-to-many, we can also have many-to-one as well, right? So for example, in some cases, we may have multiple inputs or we have an input with a sequence structure. Then we try to generate one single output for this kind of problem. Then we can build a recurrent neural net with multiple inputs, which will be in a sequential order, right? And we can generate one single output based on neuron for the last inputs actually. So for example, if we were starting some video classification, we know this video can be represented as a sequence of images, right? And we can provide each image as input for one of the portal here. And the main target for this problem will be to classify these videos into different categories or different classes. In other words, we try to generate one single label for its whole inputs, right? If so, then we can build this model like this. We can have multiple inputs, each input for one image, and it will be in a sequential order. And we can also have multiple hidden neurons. And for the neuron in the last output, we can generate one single label for the whole video, right? And if we are starting some problem like this, then we can build an RNN in the structure like this. And sometimes we may also start some problem for the generation of multiple outputs based on the multiple inputs. For example, for the translation, right? We can have the input of one sentence in a language and try to translate it into another language. So we know the words or the sentence may be represented as a sequence of words for both the inputs and the outputs, right? So if we do the translation, we can provide the inputs as multiple words in a sequential order. Then we can build a recurrent neural net as something like this. We have a hidden layer. However, for the hidden layer, they will receive all the inputs, and based on the representation we learn from all the inputs, we can further generate all the outputs, right? And you may also wonder why we have to adjust its position of the neurons to the right-hand side. The main reason is because when we do the translation, right, when we translate this input sentence into another one, it really depends on the language, right? Normally, we have to ensure the model will receive all the inputs until it will generate the first word as a translation result. For example, when the model translates the first word for the output, like this word, it will receive all the inputs. In other words, it will know all the information from the input sentence, right, before we generate the first word for the result in translation. That's the reason why we have to adjust the position for the output neurons to the right-hand side until we receive all the input for the input sentence. And now if we do the translation of sentences, then we can build a recurrent neural net, some structure like this, right? And besides this one, we can also have some other recurrent neural net with many-to-many, like shown on the right-hand side. Now here, if we are studying the per frame video classification, in other words, we want to classify for each image or each image frame in the video, and we want to assign them with the corresponding labels. If so, then we can have this recurrent neural net with structure like this. We have multiple inputs, also multiple outputs. So we need to ensure that for each image frame in the video input, we will have then its representation also generate its corresponding outputs. However, for the following images, it will receive both information from the raw inputs, also the representation we know from the previous inputs as well. If so, then we can build a recurrent neural net like this. It will have multiple inputs, however, it will have a corresponding relationship between the inputs and the outputs, right? So like this one can be used for the per frame video classification, a sequence images to the sequence of labels. So these are the different structures of the recurrent neural net we can use or we can build for specific application problems in the real world. It really depends on the problem we are studying, then we can build this recurrent neural net in different architectures. So I have to say here again, for the deep learning models we are studying in this course, all the model architectures are very flexible. Depending on your application task as well as the problem you are studying, then you can build this deep learning model in different forms or adjust its structure slightly according to your application problem. They are all flexible actually. So this is the recurrent neural net. For understanding this recurrent neural net, you need to understand the formulas we show in this page, how to calculate the representation for both the hidden layers as well as the output layers. So the formula we show here are just for the recurrent neural net with one single hidden layer. When we have multiple hidden layers, the calculation process will be very similar. So many of the parameters will be shared for the input layers, for the output layers, as well as for the hidden layers. Okay, so this is the recurrent neural net. Next, we can move to how to utilize the recurrent neural net for specific application problems as you will be studying for your project stage 4.